Hello, this is Shula from shulatutoring.com, and in today's video, we will go over Hardy-Weinberg equilibrium. So if you look at the description for this video, you will see that I posted a practice test. So I want you to first do the problems in that practice test, and then you can watch this video and see if you got your answers right. So first, I will go over Hardy-Weinberg equilibrium, and after the introduction, we will solve the problems. So Hardy-Weinberg equilibrium is a model that is used to predict allele and genotype frequencies in a population. So we say that P is a frequency of dominant allele, and Q is a frequency of recessive allele. And P plus Q, like the sum of P and Q, has to equal 1. And then P squared would be the frequency of homozygous dominant genotype. 2PQ is a frequency of heterozygous genotype. When we have individuals that have both alleles, that's heterozygous. And then Q squared is the frequency of homozygous recessive genotype, and the frequencies of those genotypes has to add up to 1. If you want to solve Hardy-Weinberg equilibrium problems, it's really, really important that you know those two formulas and that you know what each term stands for. Hardy-Weinberg equilibrium makes a few very important assumptions because Hardy-Weinberg equilibrium model assumes that allele frequencies do not change from one generation to another. The problem is that we live in a world that has constant changes happening, and allele frequencies actually do change, but they change because of certain factors that we are aware of. So for us to use this model, we have to assume that those factors are just not there. They're not happening. So we have to assume that there is no mutation, right? Because mutations actually change genes. We have to assume that mating is random. So when individuals mate, they do not prefer individuals with certain genes. We have to assume that there is no natural selection, because natural selection means that because of some conditions in the environment, certain genes will be beneficial or harmful to individuals, which will lead to changes in genetic makeup of their offspring. So we have to assume that there is no natural selection. We have to assume that there is no gene flow, meaning that genes, like new genes, new alleles, are not entering this population, and genes or alleles are not exiting the population. When you have small populations, some alleles can just disappear over time because of just random chance. This is called genetic drift. And genetic drift generally doesn't happen with really, really large populations. So that's why we are assuming that our population size is really, really large. So that's the introduction. And now we will go ahead and solve the problems that I posted. Again, it's much, much better if you actually do the problems first rather than just watch me do the problems. So I strongly encourage you to do that. So cystic fibrosis is an autosomal recessive disorder. It affects 1 out of 2,500 newborns of Northern European ancestry. What is the frequency of carriers of this disease in this population? If for Hardy-Weinberg equilibrium problems, it's very important to understand what we're given and what we're asked to find in terms of P and Q. So we are given this number, 1 out of 2,500. What does this number stand for? Well, we know that it's the number of affected individuals, and they're affected with this recessive disorder. Two key words here are affected and recessive. For recessive disorders, the only individuals that are affected are homozygous recessive. Homozygous recessive. So 1 out of 2,500 is the frequency of homozygous recessive. According to our formulas, the frequency of homozygous recessive is given by Q squared. Okay, so we are given Q squared, and what are we asked to find? We're asked to find the frequency of carriers. Carriers are individuals that will have this recessive gene, but will not express it. That would be the heterozygous individuals. So that is the 2PQ that we're being asked to find. So far we have the Q squared, and we need to find just the Q and the P. So let's start with the Q. So to find Q, we need to square root both sides. So Q is 1 out of 51 divided by 50. If we convert it to a decimal form, we get 0.02. So that's our Q. To find P, we always use this formula. So if Q is 0.02, that means that P, if we subtract 0.02 from both sides, that P is equal to 0.98. So now all we need to do is multiply those numbers together. 2 times 0.98 times 0.02 is what? I got 0.0392. If you want to convert it to percentage, all you do, you multiply the frequency by 100, and then you get 3.92%. So if you got this number, congratulations, you can give yourself 12 points. You got it right. And now let's do the next one. So population of tropical plants exhibits incomplete dominance with respect to petal flower. Homozygous plants are either yellow or red, while heterozygotes are orange. If we know the frequency of the red allele is 0.4 and the population size is 200, how many yellow, red, and orange plants should we expect to find? First of all, what is incomplete dominance? It's different from the regular dominant and recessive pattern, in which when you have just, dominant and recessive, when you have two of them together, like you have 2PQ, right? You have a heterozygous genotype, the dominant will mask the effect of the recessive, and the recessive won't be expressed. Well, here, when you have incomplete dominance, you basically have two alleles that are exerting the same effect. So when they are together, when you have heterozygous genotype, you get an intermediate phenotype. So when you have incomplete dominance, you can just assign alleles to P and Q, right? Because generally we use Q for recessive and P for dominant. Here we have basically two dominants or two incompletely dominant alleles. So you just assign one to P and the other to Q, but make sure you stick to whatever you assign it to, right? You cannot switch it in the middle. So I'm choosing that P is going to be red allele, right? The frequency of red allele. And Q is going to be the frequency of yellow allele. So now what are we given? we're given that the frequency of red allele is 0.4, meaning that P is 0.4. Well, Q has to be 0.6 because P plus Q is 1. So now we need to find the actual numbers of yellow, red, and orange plants. The number of plants in each category would be frequency multiplied by total number. So we need to find frequencies for each. So let's say here we have red, then we have orange, then we have yellow. So let's say here we'll have frequencies, and now we have numbers. So I'll make a little table here. Okay, so for frequency for red would be P squared, right? Because that's the frequency of a homozygous dominant. The frequency of orange would be 2pq. That's the frequency of heterozygous genotype. And the frequency of yellow would be q squared. And how do we calculate this? Well, p squared would be 0.4 squared, would be 0.16. 2pq would be 2 times 0.4 times 0.6. And q squared would be 0.6 squared. So let's calculate this. 0.4 times 0.6 would be 0.24. I got 0.48. And here I get 0.36. So those are our frequencies. To find the actual numbers, we have to multiply the frequencies by the total number. So 0.16 times 200 would be 32. And then 0.48 times 200 would be 96. And then 0.36 times 200 would be 72. So let's add up those numbers, 32 and 96 and 72, because they have to add up to 200. And yes, they add up to 200. That's a very good way to check yourself. In terms of frequencies, once you get your frequencies, a very good way to check yourself is to just add up those frequencies, because they have to add up to 1. So we got the numbers of red, right, the orange, and the yellow. So if you got those numbers, give yourself 12 points. If you got to this part, at least, give yourself partial credit. And let's continue to the next one. In a population of squirrels, black coat color is dominant over gray coat color. If 153 out of 300 are black, how many squirrels have homozygous dominant genotype? So we are given this number. 153 over 300 are black. That would be all the squirrels that are expressing the dominant allele. Well, the problem is that that includes both the heterozygous squirrels and homozygous squirrels. And we need to find a way to find just the homozygous dominant. All right, so that would be p squared plus 2pq. We need to take this part out. So how do we do that? Well, let's think about it. If 153 squirrels are black, it means that the rest of them are gray. And all the gray squirrels have to have homozygous recessive genotype. So 300 minus 153 is 147. And then 147 out of 300 would be 0.49. That is actually our Q squared. So Q squared is 0.49. So that's already something. We are being asked to find P squared. So we have to go from Q squared to P squared. Let's first find Q. So to find Q, we need to square root both sides. And the square root of 0.49 is 0.7. So we know that P plus Q is equal to 1. So that means that P has to be 0.3. And now we just need to find P squared. P squared is equal to 0.3 squared, and that is equal to 0.09. We're not done here because we're being asked for the number of squirrels. So now we need to multiply the frequency by the total number. So number of homozygous dominant would be 0.09 times 300. So that would be 27. So we have 27 squirrels that are homozygous dominant. So if you received 27 as your answer, please give yourself 12 points. If you got to this part, to the frequency part, give yourself partial credit. And let's just do our true or false questions. So the first one, the frequency of homozygous dominant is P. Well, we know that the frequency of homozygous dominant is P squared. Right, so that is false. The Hardy-Weinberg model assumes that there is no mutation. This is true because mutations change genes, so we're assuming that there is no mutation. If P is 0.4, then Q must be 0.6, while P and Q add up to 1, so that is true. Individuals with heterozygous genotype always express both alleles. No, it's false, because if you have dominant and recessive and you are heterozygous, you will not express the recessive allele. Non-random mating affects allele frequencies. That's true because certain alleles are being preferred over other alleles. One of the assumptions of the Hardy-Weinberg model is that the population must be at carrying capacity. This is not one of the assumptions. Carrying capacity is a term from ecology. It's referring to the maximum number of individuals in a population that an environment can sustain. So this is false. So please score your points and you can calculate your grade. Once you calculate your grade, you can mention it in the comments. I hope it was helpful to you. And I'll be coming out with more videos like this. I'll be making practice exams on different topics in biology and chemistry. And then I'll be providing like videos with explanation. So I hope you enjoyed this video. If you did, please like this video and subscribe to my channel so that you don't miss future content. So I hope I'll see you in the next videos. Bye-bye.